Hello everyone and welcome back. So today let us first discuss about the solutions to the problems that I have given in the previous lecture based on isomorphic graphs. You were provided with 4 graphs G1, G2, G3, G4 and you were asked to check which of these pairs of graphs are isomorphic to each other and which are not. So separately we will discuss for each pair of graphs here. Now when you observe these graphs, you will find G1 is a bipartite graph. If you compare the order, size and degree sequence, you will find every graph presented here is having the order 6, every graph is having size 9 and every graph is a regular graph with vertex degree being 3. Now let us compare the graphs G1, G2. If you try to redraw the graph G2 in the bipartite structure, you will find G2 can be drawn as a bipartite graph and it will look exactly the same as the graph G1. That is, G1 and G2 will be isomorphic graphs. That you can check yourself just the way we have solved in the previous lecture. Similarly, you will find that G3 cannot be drawn as a bipartite graph. It doesn't have that bipartite structure. You will get stuck and that is the reason G1 and G3 definitely are not isomorphic, because G1 being a bipartite graph, it will be isomorphic to a graph that has to be bipartite first of all. So definitely G1 is not isomorphic to G3. Again, if you try to redraw G4, you will find it has the bipartite structure and it can be drawn exactly as the graph G1. So G1 is isomorphic to G4 as well. So that you can check yourself. So here I have listed down the results. You will find G1 is isomorphic to G2, G1 is isomorphic to G4, but G1 is not isomorphic to G3. Now from the first two results, definitely you can see G1 is isomorphic to both the graphs G2 and G4. That indicates G2 and G4 must be isomorphic to each other as well, because both are the same graphs as G1. So they must be same themselves. So that concludes G2 is isomorphic to G4. Now G1 being isomorphic to G2 but G1 not being isomorphic to G3 indicates G2 and G3 definitely must not be isomorphic graphs, hence this conclusion. Lastly, again for similar reason, since G1 is isomorphic to G4 but G1 is not isomorphic to G3, that is from these two results you can conclude that G3 is not isomorphic to G4. So basically comparing the graph G1 with all the other 3 graphs, we can basically get all the conclusions that we need. So you can try to solve this yourself. These are the results. Still, if you face any doubt while checking for any particular pair of graphs among these, then please do comment below. We will definitely try to help you with the solution to that corresponding problem. Now today we are going to discuss some non-isomorphic graphs of different orders, and in particular we will talk about a specific type of graph, that is the self-complementary graph. So we will see here what are all those graphs who are having the order 2 and are non-isomorphic to each other. So basically we are trying to find all the graphs that we can draw having order 2, that is with 2 vertices, but they will be non-isomorphic to each other. They will be different graphs. You cannot draw any one of them in the same structure as the other. So they have to be non-isomorphic. In how many ways can you draw such graphs of order 2? So that is our question basically. And do remember, we are dealing with simple graphs only in the entire concept of isomorphism. So here our job is to draw simple graphs having order 2. So the very first example of a simple graph having order 2 is this particular graph, which is edgeless. It doesn't have any edge. Another simple graph that we can draw with order 2 is the graph with a single edge. And in no other way can I draw a simple graph with 2 vertices. These are all. Now if you compare these two graphs G1 and G2, we can immediately say G1 is non-isomorphic to G2. Reason? G1 is edgeless whereas G2 is having an edge. So their size doesn't match and therefore they are non-isomorphic to each other. So we have a pair of non-isomorphic graphs of order 2. So there is only one pair of non-isomorphic graphs of order 2, which are presented in this slide as well. Next, we will try to find out all the non-isomorphic graphs of order 3. So basically we need to draw all the simple graphs that we can having order 3, but the graphs would be non-isomorphic to each other. Let's see how we can do that. So if the graph has to have an order 3, so there should be 3 vertices in the graph. So the very first graph that I am going to draw is the edgeless graph. So this is a graph with order 3 with no edges. Next I will draw another simple graph with 3 vertices but non-isomorphic with G1. So definitely drawing another edgeless graph of order 3 is not going to help. It should be non-isomorphic to G1. So what I will do is I will draw one edge only between any 2 vertices. So this graph G2 definitely is non-isomorphic to G1 because their size doesn't match. What else I can do? I can have a simple graph of order 3 with 2 edges now. For example, this is G3. Again, see, G3 is non-isomorphic to G1 because G3 is having 2 edges whereas G1 is having no edge. G2 is non-isomorphic to G3 because G2 is having only 1 edge, G3 is having 2 edges. So all these 3 graphs, G1, G2 and G3, are mutually non-isomorphic to each other because all of them are having different size. You are basically searching for graphs which are non-isomorphic to each other. So whatever next graph I am going to draw, G4, it would be such that it is non-isomorphic to each of the previous graphs G3, G2 and G1. Okay. So what else I can do with 3 vertices? Now I can draw 3 edges. So this is another graph that is non-isomorphic to all the other existing graphs. That is G1 is non-isomorphic to G2, which is non-isomorphic to G3 and which is non-isomorphic to G4. So we have a set of 4 non-isomorphic graphs, each having order 3. We don't have any other graph of order 3 that will be non-isomorphic to all these 4 graphs. Okay, so this is it. So there are 4 non-isomorphic graphs of order 3, one with no edges, another with a single edge, the other one with 2 edges, and lastly the one with all the 3 edges, the complete graph. So you can keep in mind that while creating the non-isomorphic graphs of a certain order, you should start with the graph having no edges and you should end with a graph having all the possible edges, considering the graph to be simple. That is, you start with the edgeless graph and end it with the complete graph of that particular order. Let's see for the next non-isomorphic graphs of order 4. So now we will be dealing with graphs of order 4. So there are 4 vertices with you. So I'll start with the edgeless graph G1. Next I will have another graph of order 4 where I will insert one edge only. That is my G2. Definitely G1 is non-isomorphic to G2. Next, I will have another simple graph of order 4 where I will insert 2 edges. That is G3. Now you see, the way I have inserted 2 edges in the graph G3 is different from the way I am inserting 2 edges in the graph G4. See, are G3 and G4 isomorphic graphs? No. G3 is non-isomorphic to G4. Although their order, their size is same, they are non-isomorphic because I have a very simple reason. In G3 I have a vertex of degree 2, this is a vertex of degree 2, but in G4 there is no vertex of degree 2, there are all the 4 pendant vertices. So definitely the degree sequence doesn't match. The degree sequence of G3 is 2, 1, 1, 0, whereas the degree sequence of the graph G4 is 1, 1, 1, 1. So they are non-isomorphic graphs. So although 2 edges are inserted, but they are inserted in different manner, in completely different format. So definitely they are non-isomorphic to each other. Next, I can draw another simple graph on 4 vertices by inserting 3 edges now. So this is a way of inserting 3 edges in the graph. What else I can do? With 3 edges only, I can have another graph. For example, I make these 2 adjacent, these 2 and these 2. That is a P4. And if you observe carefully, you will find G5 and G6 definitely are non-isomorphic graphs, again because their degree sequence doesn't match. The degree sequence for G5 is 3, 1, 1, 1, whereas the degree sequence for G6 is 2, 2, 1, 1. So they are non-isomorphic graphs. See, the 6 graphs that we have drawn so far, every pair among these 6 is a pair of non-isomorphic graphs. We proceed further and let's see if we can draw any more such graphs. So with order 4 and with 3 edges, again I could have drawn the graph like this as well, G7. See, how come G7 is non-isomorphic to G6? My reason would be G7 is having one isolated vertex, but G6 has no isolated vertex. So G7 is another non-isomorphic graph in this list. Next, we no longer have any other non-isomorphic graph with 3 edges on 4 vertices. So now we will move to simple graphs of order 4 having 4 edges. So one way of having 4 edges is this one, that is G8. Next, we can have the 4 edges like this also, G9. Clearly G9 is different from G8. G9 is having a C3 that G8 doesn't have. G8 is having a C4 that G9 doesn't have. You can see their degree sequence is different. So they are non-isomorphic graphs. Next, I do not have any other more graph where I can have 4 edges in a different pattern. so that they are non-isomorphic. So I go to insert 5 edges now. So to have 5 edges, the only possible way for me is to have a graph like this, G10. This is the only way to have a simple graph of order 4 and size 5. Next, and the last one definitely, because now I am going to have the complete graph, that is the K4, which is having 6 edges in total. This is G11. So I have started with the edgeless graph and I am ending with the complete graph on 4 vertices. So these are all the 11 non-isomorphic graphs of order 4. I have listed all of them clearly in this slide. You can check on your own. You will find every 2 graphs from this list are non-isomorphic to each other. No 2 graphs among these would be isomorphic. Okay. Next, we come to the very important concept of self-complementary graphs. What is self-complementary graph? As the name is suggesting, you can remember it that way. A self-complementary graph, as goes the definition, is a graph which is isomorphic to its own complement. That means, given a graph G, if you want to check whether it is a self-complementary graph or not, you need to draw the complement of the graph, that is G bar, G complement, and you need to check whether G and G complement are isomorphic to each other or not, because now you will be having a pair of graphs, the original graph G and the complement graph G complement. You know how to draw the complement of the graph. So now you have a pair of graphs. Check whether they are isomorphic graphs or not. If they turn out to be isomorphic, then we will say G is a self-complementary graph. In a similar manner, we can also say G complement is a self-complementary graph, because the complement of G complement is the graph G itself. So if they are isomorphic to each other, the graph will be called a self-complementary graph. And this is how we present it. G is isomorphic to G complement if it is self-complementary. Now let's see with the help of some examples. The very first example of a self-complementary graph that I will give to you is P4. So this is a P4. Now what will the complement of P4 look like? The complement of P4 also will have all the 4 vertices. The edges that are present in P4 will not be present in the complement, whereas the edges which are not present in P4 definitely would be present in the complement. So this is the complement of P4. Now in order to check whether they are isomorphic to each other or not, let me label the vertices. So here I am having suppose A, B, C, D, and here you are having U, V, W, X. Now to check the isomorphic property, let me redraw, for example, say the graph P4 and see if P4 can be drawn in the same structure as P4 complement. So what I will do is, on behalf of the vertex U, since U is a pendant vertex, so let me put the vertex A at that position, because A is also a pendant vertex in P4. So that can match to the vertex U. Now A is adjacent to B, so the neighbor of U is present here as V. So I will also draw the neighbor of A, that is B, at this particular location, so that structure wise it looks like P4 complement. Okay. Next, B is adjacent to C. So as per the figure of P4 complement, C should be here. Again, C is adjacent to D in the graph, so the vertex D should be here. So I can see I can redraw P4 maintaining its adjacencies, but orientation wise it looks like P4 complement entirely. That means P4 is isomorphic to its complement P4 complement. That means P4 is a self-complementary graph. Let's go through another example. Suppose I take C5. C5 is the cycle of length 5. This is C5. So what is C5 complement? It is also the graph on 5 vertices. It will contain the edges that C5 doesn't have, and it will not contain any of the edges that C5 has. So basically if you draw the complement, you are going to get this particular graph. Now to check whether C5 is self-complementary, I need to check whether C5 is isomorphic to C5 complement, that is whether these 2 graphs on this slide are isomorphic to each other or not. So let me label the vertices first. Now let us check whether they are isomorphic. How to check? I will just redraw one of the graphs in terms of the other. So what I can do is, suppose I pick C5 and I want to redraw it. So in the position of the vertex V, I can put the vertex V, because that is also having degree 2. Basically all the vertices here are having degree 2. Now let me redraw C5 and keep an eye on the structure of C5 complement and just keep drawing. So B is adjacent to the vertex A and the vertex C. So the 2 neighbors of B should be present as the neighbors of V are present in C5 complement. So I place A here, I place C here. A is adjacent to the vertex E. So I keep the vertex E here. E is adjacent to the vertex D, so I keep the vertex D here. And D and C are adjacent, so I make the vertices C and D adjacent to each other. So I can see that C5 in a different orientation look exactly like C5 complement. That is, C5 is isomorphic to C5 complement, so C5 is a self-complementary graph. And when they are isomorphic, you can definitely provide the isomorphism as well, the bijective mapping. So that is basically the idea of self-complementary graphs. So that's all for today. I am going to meet you again soon with the next lecture of the series. Till then, if you face any problem, any confusion, any doubt regarding any concept, please do write to us in the comment section below. We'll definitely try to solve your problems. Besides, if you love learning with me, then please do like, share and subscribe to our channel. Till then, thanks for watching. Take care and bye-bye.